Evening, everybody. On behalf of my co-host, Kevin Mitchell, and the UK Synesthesia Association, our sponsors, Movidius, and our colleagues here in Science Gallery in Dublin, we would like to welcome you to this talk tonight. My name is Fiona Newell, and I'm here to introduce tonight's speaker. But before I do that, I wanted to give you a sort of historical context and a very much local context to tonight's talk. In the 18th century, Dublin had lots of coffee houses, and coffee houses were the hubs of intellectual activity at that time, more than 300 years ago. And one of the conversations that occurred, particularly in a coffee house known as Dick's Coffee House, which was at the back of Christ Church Cathedral, for those of you who know Dublin, a conversation occurred in there. And it started off with a question posed by William Molyneux, who was a politician and a philosopher then. Don't get that mixed much these days. But, and he posed the question, which we now know today as the classic Molyneux's problem. And his question went like this. He wondered whether if a man who was born blind and could suddenly learn to see, could that person be able to discriminate between the shape of a sphere and the shape of a cube? So he posed that question to John Locke, who was an eminent British philosopher at the time, in 1688. But it caused a lot of conversations here in Dublin, in these coffee houses, and that particular question inspired a young philosopher, George Berkeley, who later became a fellow here in Trinity College. And he was particularly inspired by that question. And it took him a while, but in 1709, he published an essay on a new theory of vision, where after contemplating this question, he concluded that there is no direct connections between the senses, that any connections there are between the senses, that exist between the senses, have to be acquired through experience. Now, his thinking and Molyneux's problem has really formed the basis of a lot of modern research into multisensory integration, including my own here in Trinity College. So moving rapidly along to tonight's talk, 300 years later, a little bit slow, Amir, but still in the same place, here in Dublin, I'm very pleased to have Professor Amir Amedi join us tonight. He uses unique tools known as sensory substitution devices to take information from one sense and present it to another sense. And his research has had profound insight into how the brain uses sensory information in order to perceive the world. And Amir is an associate professor at the Department of Medical Neurobiology in the Hebrew University in Israel. He's also an adjunct research professor at the Sorbonne in Paris. He holds a PhD in computational neuroscience. He's a postdoc and an instructor of neurology at Harvard Medical School. He's internationally recognized and acclaimed for the work that he does on sensory integration in the brain. He's received many prizes for his work to date and on our understanding of the sensory regions of the brain. I've known him for many years. I met him, I think, when you were a PhD student and I was a postdoc. I won't say how many years ago that was. But it wasn't until yesterday that I discovered that actually he's a keen musician and he plays the saxophone. And he once considered a career in music. Well, music's loss is our gain, but he hasn't lost music too much. He still incorporates music into his research. And he's going to explain how he's done that in his talk, which is entitled Restoring Functions Lost in Damaged Senses and Creating New Senses. Please join me in warmly welcoming our speaker tonight, Professor Amir Amedi.
Thank you very much, Fiona and Kevin, for the invitation and for the very kind intro. I'm very excited to be here and see so many friends and familiar faces and some faces that is less familiar. I want to start. postdocs and master student in the lab. Especially, I'm going to present the work of last Amir Amedi, Sami Aboud, Shachar Mandenbaum, Lior Reich, and Roni Arbel, and also a collaboration with José Sahel, the head of the Institut de la Vision in Paris, Laurent Cohen, and Stanislas Dihan, all from Paris. There is a bit of a hum, yeah. Is it okay? Okay, excellent. So, on the verge of a revolution that is happening these days, and I'm not sure how many are aware of it, although it's happening more and more in the media, and we can see it. There are over here because it's a little bit off topic, but it's a deep brain stimulation in which you can take a person that is having difficulty to hold for it. Of course, kinds of implants. My point is we are going to see much more cases in a lot of clinical cases, but maybe not only clinical cases. And it's going to be part of our life, maybe of most of the people in like 50 years, I don't know. The thing is that it looks like a miracle, but there is a lot of issues with the way that interfacing with our brain at the moment is being carried over. The animal studies, but my prediction is that it's going to be, again, part of our life more and more. If this were animals basically ask as scientists and society and so on and so forth. So this will be the hard to highlight it in the head, might not. So we're going to have more and more people suffering for a visual loss due to age. And the most exciting line of research in terms of restoring the like everything in life, now it starts to get more complex and more complicated, because what happens is that somehow the brain finds it very beyond light. Okay, so for we do a lot of rehab. Usually it's a visual rehab, and after half a year, if you're really lucky, or 1 year, so this is really not that great, right? So okay, that's maybe the bottom line. So, and so this is the meter when we perceive as blue, getting closer to 700, it's becoming reddish, and it's converted. it's a bit strange. I saw it so many times, and I started to. Scientists that came to the conference with these 3-4 examples. Can participate, by the way. The entire experience of this logo. And again, the input to your eyes didn't change at all, right? It's remained on the screen exactly the same. Okay, so our visual system, the point is this, based on all of our history, our visual experience is shaping up by our brain and by prior experiences. Maybe a bit more vivid experience is, so we see with our brain not less than we see with our eyes. Another thing is something that was went way up circles, and this is this example of the dress. So let's try to do a little experiments. Sometimes it's working better, sometimes less. It depends on the lighting condition, but let's try to do this little experiment together and gather some statistics here. So. You remember that a minute ago we said that we see color by whether if it's 400 nanometer or 500 or 700, right? If it's blue or reddish and so on and so forth. So let's look at this middle dress and tell me how many of you see it like me in white and gold. Just raise your hand. So yeah, I already see it's going to be a little bit of a problem, but is anyone in the audience see this dress now in blue and black colors? Oh, I'm relieved. So it's actually about the internet. It created chaos, okay, because people were starting to fight, and actually. Three different lighting conditions. But we just did an experiment that shows that this was not the source of this difference of experiencing colors, because you saw that all of you and about half of the audience see it in blue and black, so both grayscale, yeah, we have black and blue, and the other half see it much more in reddish color in gold and in white. So how can it be? Okay, so let's try. I know, I can ask, after that we can argue about it and try to explain how this is happening, that we, even objects we saw in a moment, colors we see differently. I would just show you that even grayscale things we saw based not on the visual input but on the context, okay? And this will actually help us to understand this dress thing. So you see here a gray line, okay? And actually, if you look at this side, is it which side is darker and which side is lighter? Is the right? Who thinks the right side is darker? Yeah, everyone. And who thinks the others? Yeah, and so on and so forth. But the point is that actually the line have exactly the same grayscale, and if the environment. So it have nothing to do with the physics of the stimulus. It have something to do with the physics, of course, but also of the surrounding and the context. And this is probably explanation for the dress. So let's try to explain it using this phenomena. So if we think that the dress is in the shadow, for some reason, we think that the dress is there in the shadows and not in bright light, then the brain is going to remove the blue cast, and we are being left with, remove the darkish color, and we are being left with white and gold. If, on the other hand, we think the dress is washed out by very bright sunshine, then the brain is going to perceive the dress as darker blue because it's going to remove the light colors, okay? Now, okay, so the mystery is solved, right? So the thing is that this dress is a bit ambiguous. Some of you think it's in the washed by standing in a very bright sunshine, and some of you think it's in the darkness. And this is the source of perceiving the different color. Now, what we don't know exactly is why some of you think it's in bright light and some of you think it's in dark. And probably part of the reason is that all your past experiences give you a different explanatory to this ambiguous figure, okay? So the here, A and B look in dark and white, and actually they are both grayscale and so on and so forth. So the bottom line is that we see, and the point is, I don't have time in this talk, but it's exactly the same in the auditory modality and the somatosensory modality. We see, we hear, and we touch with our brains, not less than we see with our eyes. Objects, color, grayscale. Most of the time, it looks so trivial that actually we don't pay attention to all these processes that are happening in the brain, but they shape the way that we see. Maybe the last example I want to give, especially to the general public, because I think maybe it's the coolest phenomena that show us that we create the outer world, not less than we perceive it, is this little thought experiment. Let's start by taking our fingers and putting them close to our nose and closing the right and the left eye, and then putting them the same trick, okay? So all of you would see that we actually see very similar picture with the two eyes, but there is the finger jumps more in one position versus the other. Where does it jump more, when it's close or when it's far away? Close. When it's close, exactly. So we have a 3D universe. You are in 3D, right? But it falls on our eyes in 2D. So our eyes get only 2D information, and actually the brain creates an illusion of 3D that now I see you in 3D, but this is only an illusion that my brain creates by computing how much discrepancy there is between the two images. If the and the avatar are creating their movies, they look into the vision scientist and to all the evidence and create by computations this illusion of a frog coming from here to here, so they would change the discrepancy, okay? But this, so usually we have these two pictures a little bit different, and we compute the 3D. But what happened with this thought experiment, and this is not for the scientists in the audience, but for the general public. Let's do a little thought experiment, and say I have these special glasses that I can project you to the right eye, this image of Tomer, yeah, and this is a not so hidden advertisement. He's the head chef of the Palomar. It's a really good restaurant in London that we are all very proud of him. And let's say I'm putting him on the right eye, and on the left eye I'm going to put one of his dishes, this beautiful polenta. So what do you think? Raise your hand and try to give some hypothesis. Try to be a scientist and give some hypothesis what will happen to our perception. So instead of having two images that are the same but just a little bit different by the depth, let's now give one picture to one eye and another picture to the other eye. A person and food to the other eye. Anyone want to speculate what will happen? Not you, Fiona? Yes?
The two pictures will just merge?
Exactly. So the first and most basic hypothesis is it will be some chimeric experiences, and we will see the polenta and Tomer together at the same time. It's a very good hypothesis, but it's not what's happening. Another hypothesis, yeah?
You see whichever picture your dominant eye is on.
Very good, very good. If you, I don't know if all of you know what is your dominant eye, but if you want to find out what is your dominant eye, put a little circle and put I'm standing here, so it will have to be me. Put me on and see me on this little circle. And now close one eye and close the other. In the eye that you see me inside this hole is your dominant eye, okay? So actually we can do, if this is the we're very good for statistics, this audience. So eye, okay? This is not what's happening. So let me tell you a lot of fun, 7, 8 hypotheses. This is what we do as scientists. We do hypotheses, we think about what's the outcome, and then we go and do the experiment. And when you do the experiment, something really extraordinary happens and really proves that we don't see only with our eyes, but we see with our brain. So what happens is that you would see, for a brief of a second, you won't see anything, and then out of the darkness, out of nothing, one of the images will come, and it will be quite random. Let's say it's Tomer. And then you would ignore, your brain completely ignore the polenta, and it won't be existing in the world at all. But it will only happen for 8 seconds, about 8 seconds. And you would see the polenta, like there is no Tomer in the world. And this will continue forever, as long as we continue to project these two images. So really this proves that, and you can switch the images to Tomer's lovely wife, which is the head of desserts and a different food, and it will be exactly the same. So said, hey, if this is what's going on, why don't we make a bypass? And he mainly uses tactile sensory substitution, and his idea was the following. If the blind is going to look with a camera on this letter V, for example, or this book, or this whatever, we are going to project information that is a topographic information into the tactile modality on the tongue, on the hand, on the neck, and we are going to draw vibrators on the back, and I can he could stimulate this letter V, and you would experience the letter V. You can do it to your, after that, on the back. So, and it started with very simple stimuli like this, but we can do more and more, he did more and more complex stuff, and basically convey the information into the brain, into this half of the glass that is full, and train the brain to understand the information coming from a different sense. We focused in the last several years on auditory sensory substitution. It's a little bit more difficult to understand. We worked with both the voice by Peter Mayer and the iMusic that we developed using music information. And basically, there is a lot of advantages for research, but maybe beyond, because actually you don't need to build a lot of very complex and very expensive devices, and also you are very limited in the somatosensory modality by your 2-point discrimination on the back, for example. If the points are less than 4 centimeters apart, then you wouldn't be able to recognize anything with this resolution, okay? Of course, it's very comfortable to the research because we can see what happened in the brain while subjects learn to do it, and so on and so forth. Actually, what we do in the last year or two, we actually do both. We take input from the camera and embed the information both in several tactile matrices and in the auditory domain, and we teach the blind to do it. So let's see what can you do with this type of sensory substitution. And I want you to try and understand, and I'm going to present 2 sensory substitutions. One is the iCane, which is a very simple device and very easy to learn, because this is a key part, the training and the learning. Actually, after the talk, we are going to have a little maze, and people can go and play with this maze blindfolded and try to walk with them without vision, just with the tactile modality. So basically, this is a very simple device that you can have in 1 direction or 2 direction or more. It can come standalone or with the cane. It have up to 5-meter range. And it vibrates according to the distance to the next obstacle, something that you usually would do with your visual modality, right? So, and then we are building these mazes and have people like rats going in the mazes and need to go out. I'm going to show you a movie now of a congenitally blind that had 2 minutes of training, like you are going to have in a little bit more simple maze after the talk. And you can see here that this congenitally blind It's actually twice the actual speed. You can see here Daniel Shabbat, which led this project together with Shachar Mandelbaum. You can see that very easily, in 2 minutes of training, you can already do it. We also create, and you can see that the subjects inside the scanner can navigate and try to find a way out inside this maze, and use, in this case, the auditory modality. Again, it's very easy to use it for MRI. And you can see that he gets information when he gets closer to the wall, and hop, he's out of the maze. Okay? You can see here a performance inside the scanner in different mazes, outside the scanner and inside. And you can see here something, first of all, that they can do it. They can go out of maze and you can scan their brain and look at their navigation system when they use the visual modality, the auditory modality, when people have visual experience, don't have visual experience. We'll get to it in a second. I do want to highlight one very cool result, which actually tells us what is the difference also between the senses. It's not that everything is, one of the unique properties of vision is that it's a far sensing modality, okay? So if, for example, I'm putting you in this room and I'm telling you to find this exit, what you usually do with vision, you would do 1 step or 2 steps, and then you explore this environment like I'm doing here. You would find the open door and just go. What you do with a white cane, or when you don't have a device, like the tactile modality, which is 1 meter, usually what you will do, you will just go randomly, straight or left or right, and then you would stick to one of these walls and just walk until you find the exit and go out. And this is the same thing with the white cane when you 1 meter, so you go, you find the wall, and you go out. What you do with this device, which is up to 5 meters, you will do something that is now starts to resemble vision and the mobility patterns of vision. You will go 1 step, explore the environment with the cane, find the exit, and go out. Okay? So it shows us that by teaching these far sensing abilities, you can start using the auditory modality in a way that is much more similar to vision. Okay? And we also image the brain. You can see here subjects before training and after training of particular maze. And you can see that they manage to navigate their way out using their vision modality or their auditory modality. And it can be blindfold subjects, just like you, or it can be a congenitally blind that develop the brain without any visual experience. And we can look what happened in the brain in various cases. And this is data from Shachar Mandelbaum. We'll get to this in a minute. But before we get into what happened in the brain when subjects learn to see, quote unquote, using their other modalities, I want to do for 5 minutes a little bit of training and try to teach you to read 1 or 2 letters or maybe even a whole word using music and the auditory modality. So are you ready for this? Okay, so let's give it a try. Like a choir that might have soprano, might have tenor, might have bass. The image is being scanned from left to right, and if there is very bright pixels, it will have loud sounds. If it have dark pixels, it will have very low sounds. If it's completely dark, there is nothing, okay? So let's see one example. Okay, so this is stairs down or down. You can hear this human voice. Of course, it's not nice like a Mozart piece, but it's still kind of you can hear that it's a human voice and it's nice. And the line goes down. Now, and by the way, dots and lines. So we basically teach them by the hierarchy of the visual system. We start with dots and very simple lines, and now then we will combine 2 lines, and then it will become more and more interesting. Okay? So let's start. So we did diagonal line. What about the horizontal line? Just a second. You see it's very pure and very high, but now if we are going lower, it's going to be a bass, okay? And you can learn exactly the height of the sound according to the height of the musical singing notes. Okay, now we are going to have test number 1. I'm going to play to you something, and you have to guess what it is, okay? So try to draw. Very good. So it's a diagonal line going up. Very good. Now let's move to level 2. Okay, this is level 1. Let's try actually one of the most difficult letters, and this is the letter H. Okay, so what happened in the letter H? You have the vertical line, which is a lot of sounds at the same time, so it's very dirty, and then out of it will be this mid-level tone that is much more pure. Try to listen to it, okay? Can you get it? Great. Now let's add the next step, and you are ready to read your first word. Okay? So this is the word high, okay? So you can already read, and it sounds really trivial that in 1 hour we can teach this, but I want to remind you that with visual prosthesis, it will take us 1 year or half a year to get to this stage. So you can already start imagining what's the power of combining touch, sound, and stimulation of the nervous system, which is the bottom line of what I'm trying to show here, together with what happened in the brain that I will show you in 2 minutes. But before that, we have a little exam, okay? And I'm going to show you now, play for you. I'm not going to show you, if it works, a word, and you will have to read it or write it down, okay? Don't shout it loud so everyone can try. Now, since it's really difficult, usually we'll need to take, after 1 or 2 hours of training, anyone can read any 2-letter word, or the best would read 3-letter word. But we have only 2-3 minutes, so I'm going to tell you that this word is, the first 2 letters are going to be the H and I, and then there are going to be some additional letters, okay? So you have a click, and then the soundscape, and you will have to try to read it, okay? Let's give it a try. H, I. Okay, we'll do it 5 or 6 times. H, I. Okay. 2 more times. Okay, so don't say good audience. Also half-half. Everything is half-half, but different people each time. Okay. So when I'm going to, I always dreamt to be a musician, and I'm a failed musician, but at least now I will be conductor. I'm going to do 3, 2, 1, and you're going to shout the word, okay? 3, 2, 1. Yeah. Wonderful. Let's hear it. Ti-do, ti-do. You can listen to the lower leg, okay? So very well done. Usually there is like 3, 4 people, and here about half. But now let's to see different colors, something that none of the retinal prosthetists at the moment even trying to do. Maybe they try, I don't know. But it's not possible. Now, I have to remind you that most of the photoreceptor, the huge majority, are color receptors in our eye, okay? It's about over 90% are color. So color is really important. Where is it especially important? It's especially important with our body, because we want to interact with the world. We just don't want just the blind to experience the world. We want to interact with our world. So if we could have the body colored in a different color, then we are going to have a much easier life. And this is exactly what we do with, so there is 2 modes in the eye music. One is grayscale. The other one is using color. So we can actually have the pixels that are black, no sounds, the pixels that are white with the human voices, just like we did so far. And we can add, if the pixels are red, they can have a given music instrument, in this case, piano, okay? So now the hand will stand out, and the difference between the hand and the objects, and so on and so forth. So let's demo it, and we can do the same trick with more colors. So for example, we can have 4 or 5 or 6 colors and change the levels. And the blind can learn the cross-modal correspondence. Just like in synesthesia, some people would see this music instrument or this letter in a given color. We teach them these correspondences. And you can do it. So I can show you, for example, this heel in different colors. It will sound something like this. So you can feel the topology. And now we can start drawing also a hill and have the little sunshine and so on and forth. I'm going to jump. And we can also have different setups. So we can have, for example, glasses with a camera and bone conduction sounds, or we can have this Marilyn Monroe figure. This is from the actual iMusic. And you can see that with the 1,500 pixels, we can already start recognizing faces and people if we are trained to this capacity. So in recent years, we showed that you can do reading, numbers, object recognition, body images, and so on and so forth. I'm going to show you 2 or 3 movies. This is a couple of examples, for example, from a blind going to a supermarket or looking at a congenitally blind that look at the clouds for the first time. Yeah, it's out of reach and experience it. I want to show you only 2 very quick examples. One with the voice by Peter May. You can see here, Hamutal is a congenitally blind. Just a second. You can see here the setup, the glasses that we built in the lab and the headphones. She looks at Ella, Amir Amedi, which led the imaging in the first part of the project. And you can see that by the shape, she can realize what is the facial expression of the blind. So this is after 30 or 40 hours of training. So this is generalization to a new person, okay? So this is facial expression. What about recognizing other people? So as for the first stage, we used the iMusic and created cartoons and played the Guess Who game. This is a project led by Ronnie Arbel in the lab. This is actually unpublished results, so I'm presenting them for the first time here. And basically, you would see here a congenitally blind that go through this special training for faces. He learned one set, and then he needs to recognize a new feature, understand what is the color of the hair, and also try to recognize individuals. And actually, part of this project, we try to look at the brain signal and get which object he's looking at, okay, by this auditory soundscape. But let's look for a minute how is he doing it. So you recognize some features like the bird. So actually what we did here is a little trick on Oded, is that we actually showed him somebody knows, but you change the color of the hair. And this is pretty crazy because this guy never saw colors in his life. And actually now as part of the imaging, we ask where in the brain is sorting out colors using the iMusic with music instrument and so on and so forth. But for this project, we actually ask a very simple question. Before I get into the brain imaging, which will be the last part of the talk, I'm ignoring this time and taking this time. We said 1 hour, okay? So yeah, okay. Excellent. So I want to give a little bit of an over-optimism warning. SSD are a really useful tool and great for basic science, but currently they are still not a replacement for vision. And there is a lot of issues. Insufficient information setup, there is a high cognitive load in the beginning, unlike, for example, the iCane. And so very difficult training, and we need to make the training accessible to the general public and so on and so forth. But we are actually working on it, and there is we recently reviewed some progress and challenges in these approaches. But what about the brain? What happened in the brain when the blind learn to recognize facial expression or localize to Linda or Claire and so on and so forth? So basically what we ask here is what happened in the brain when the blind, can be a blind that is anophthalmic, he never developed a retina, he never saw one form of light, or it can be a sighted that is blindfolded and doing this training like you did. What happened when he learns to recognize objects or faces and so on and so forth? We can also ask about a very interesting question. We know that we have specializations in the brain. For faces, for example, for reading, for bodies of people, and so on and so forth. So what happened to these specializations when in development in the first year, you never had visual experience, but now you experience vision, but indirectly using the auditory modality? Will we have, or the tactile modality, will we have this representation in the auditory system, the visual system? They would be in different locations, the same location that we have cited, and so on and so forth, okay? So this is basically the question. Before we get into the results, I just want to highlight several specializations we have in the brain. So for example, the most basic specialization is this specialization for faces in the fusiform face area, okay? And we have several other specializations that I will get into in a second. But actually, the most large-scale specialization we have in the brain is actually the separation to the senses. This separation that Fiona talked about, and this assumption that actually in the Molyneux problem, we have no way to transfer information between each other until we have vision, because this is different entities. And actually, the common wisdom of the neuroscience community was for many years that actually it's not only different entities in the world outside in the physical world, but also in the brain. We have all these red areas are dedicated to vision, and they process faces, reading, and everything else. And we have this blue temporal part of the side part of the brain, which processes sounds, music, language, and so on and so forth, okay? So in principle, we are supposed to have some separation here, and this soundscape is supposed to go and occupy this auditory cortex. Now, what I'm going to show you is actually, and we have a lot of other specialization after it. Even within each sense, we have a special area dedicated to human voices versus music versus language, and we have a lot of specialization in the visual modality, as I said, for objects. There is more complex maps, I won't get into them in this talk, to recognizing what are the objects, where they are located, for objects, for reading, for faces, and so on and so forth. So actually in the last several years, we went function after function, teach the blind or the sighted, the late blind, the congenital blind, each one of these functions, and try to see what happened in the brain to the specialization when they progress in the training and start being able to do what we are teaching them, to read, to recognize faces, and so on and so forth. And what happened is very consistent. And the first image I'm going to show you is this image in which we are looking at these red areas and blue areas, but actually we do a little trick that is coming from retinotopy mapping. This is a little bit technical, so it's a little bit more for the people that are using imaging, but the concept you will understand very easy. The idea is that instead of looking at reading of one or looking at of one face, we are going to repeat it many, many times. Each time we are going to repeat a word or a face, we are going to have it for about 6 or 8 seconds. You see that it's actually it's a slow motion vision, right? It took you several seconds to get the hill, right? When you get better, it takes you less, but it still will take you 3 or 4 seconds for each image. And we are going to do a rest, and we are going to repeat it many times. Then we are going to apply some mathematical method which look at where in the brain it responds to this frequency of going up and down. It's called Fourier analysis. And then we are going to have all the pixels that are going to respond in the brain, or voxels, to this frequency. But there is another trick. We can use the phase information to know when the brain responded to onset of the stimulus, when 1 second after, and when it's responded when the subject managed to say, this is clear, this is heel, this is, and so on and so forth. And what happened is really consistent is across the entire categories that we are studying, and now we have about over 50 brain scans from different subjects for a lot of categories. We see a very interesting picture that is very consistent. What you see here is that the information goes system into our hearing system, and probably what we are doing is analyzing very quickly all the heights and the power and the energy there. But then when we are trying, and this is why I'm doing this demo, because I wanted you to experience what happened in the brain when we start building the image, then actually the information is being transferred into the multisensory areas that are between them, the classical multisensory areas, but actually we are saying that everything is in a way, also the visual system is multisensory, because what happened next is that the visual system lights up at the time that we manage to build the image, okay? So actually what we are doing is taking an image, using some algorithm to encode the information about the shapes, about the colors, about the location inside sounds. we deliver it to the brain, we train the brain, and now what the brain is doing is exactly the opposite, the other direction. It's taking the sound, breaking them into all the sounds, and building the image by projecting the information back into the visual system. So this is like really miraculous, it's really cool, right? And what is really even more cool is that this happened even to the subjects, to the blind that never had any retina developed, okay? So even if you never saw it in your visual system, the information still goes there, build the topography. Vision is doing high resolution topography drawing of 2D and 3D spaces, surfaces in the world, okay? But it's actually even more interesting because what happened next is that we have other specializations. So when we recognize, for example, what is the objects, we are having the mentally blind that never had visual experience. When we're looking at the same objects and recognize where it is located, it's going to the door. Okay, this is work by last time I met in the lab. The same was replicated by Karamatsa lab for showing animate and inanimate categorization. What I want to show you is now data very, very quickly in 10 minutes, and then I'm going to summarize data in 3 main domains. One, faces, the experiment that I show you, the guess who experiment. Then we are going to look into bodies, in how we represent visual images of other people, and this is a very important ability. I would explain why. And the last portion will be about reading. When we learn to read, we have this can you hear me now? Excellent, excellent. Just, I was too relaxed, huh? So a little bit pressure is always good. So I can speed up and finish up in 9 minutes these examples. So basically we ask what is the origins of this selectivity, what is the role of visual input, the visual experience, shaping up this specialization, and we are going to also look at different functions in different evolutionary timescales. So for example, for tools and objects and faces, we had enough time in natural evolution to develop specialized areas to decode this, because we are doing it for so many tens of thousands of years and hundreds of thousands of years. But for reading, for example, which was invented only like 10,000 years ago maximum, then we don't have enough time by natural selection to develop specialization. So how come, what is the nature of this specialization? And we think that by studying this type of sensory substitution, it could be a simple sensory substitution like braille reading or this type of reading the heel, we can understand better what is the origins of this selectivity, okay? So let's do it. So we had this experiment, a block design, event-related design, and a localizer for human voices that don't have shape information. So you can recognize that I'm speaking because this is my voice, and you listen to it for 50 minutes now, okay? And so on and so forth. But you cannot build the shape. Usually you build the shape only by vision. Very rarely you do it by touch, but now we can do it also by audition. So we have faces, inverted faces, new faces, and scrambled faces. And we scan the brain when the subjects are doing this. First of all, in terms of behavior, this is a work led by Ronnie Arbel. You see they can recognize who is the character, but also can recognize if it's an upright or downright faces in 30 hours, okay? So they do this training, and now they can do it. But now what happened in the signal in the fusiform face area, okay? This is the area that dedicate to recognizing faces, and basically when you lose this area, you are losing your ability, or you're much more, you are prosopagnostic, okay? It's actually might be in other parts of this network, but basically you can recognize and see very well, but you lose this specialization, okay? And what we see is that there is a gradual activation. First of all, you see very nice response that is as nice as when sighted look at faces. This is a congenitally blind group without visual experience, looking at familiar faces, less response to unfamiliar faces, less to inverted, and scramble is the lowest. So actually, if you would give it to a visual neuroscientist, you would say this is a sighted looking at a face. But no, this is a congenitally blind
recognizing the person by the soundscapes. Next, we did a voices localizer, and you see that now the response is flat, totally flat. It's not driven by auditory input. It's driven by the fact that we build the shapes and the colors and the organization, the holistic representation in FFA. By the way, why do we have a reduction in the signal in both? This was known before in the visual modality, but now also in this new modality, in this new sense that I learned later in life. So let's look at this very quickly. It's visual illusion. I like to call it the twin Mona Lisa's experiment. And very briefly, basically, the story I invented is that there were twins, actually, Mona Lisa, not just one. One of them was brilliant, and one was, let's say, less brilliant. And the high school teacher of this Mona Lisa was suspicious that the bright one is doing the test for both of them. And he decided that he have to find out who is the differentiate between them. So can you try to differentiate between these two Mona Lisas? Yeah, give me a, yeah, what's the different? Something in the mouth, very good. Something else? Raise your hand. Yeah? Something with the eyes, yeah, the eyes turned out. Some other differences between them, yeah? Under the eyes, very good, yeah? One is not, no? Okay, I tried it, but sometimes people invent differences that are not there, which is a lot of fun. But yeah, what's happening, and I'm keeping the title, is that the face and the eyes are inverted. This is a very famous illusion. But what is really cool about this illusion is that now I'm telling you what's going on, that they are and now it's not the bright and not bright, it's something else, yeah? But now I'm telling you this is really distorted face, and I'm telling you what happened. We inverted the eyes and the mouth, yeah, that's what happened in this illusion. Now I'm telling you what happened, and we go back, and you cannot see it, okay? Why? Because we, again, evolution and experience from day one, we experience upright faces, okay? But so we are really good at differentiating these tiny differences. But when the faces are inverted, we don't have not the evolution and not the experience. But now we get exactly the same replication of this result in soundscape with people that never had visual experience. Okay, this is pretty crazy. Okay, and of course what we get in the voice areas is that all of the soundscape activate the same, and actually we get more activation by the scramble than by the real sounds of the faces. So it's a really strong double dissociation. So click on the faces. Now let's do very quickly two more areas. One is the 14 minutes, okay? We have the body area. And now this is a very important area. Why? This is when we, let's forget a little bit about this visual extrastriate body area and talk about the mirror system. This is a very important system that was discovered by Rizzolatti. And why is it very important? Because, for example, if I'm going to give you this eye cane, and this is the substitute eye cane, because the other one I forgot at home, so this is the one that was shipped in the plane. So it's the, and you will want in the demo after it to know how to operate it. What would you do, okay? So you would look at me, what I'm doing now. You would look at my visual motion. You will look at my body, and you will see that I'm activating it like this. And now, when I'm turning it into here, it will make this weird sound, right? Because it says there is something here and quiet. And now I'm turning it off. This is what we do using the mirror system. We are looking at other people's bodies and movements, and we are learning by imitation. So it's a very important mechanism. It's very well preserved in evolution. And the main input to this mirror system, if you think about it, our main input is the visualization of the body and the movement of other people. This is what is being done by the visual extrastriate body area, okay? And I want to show you that this is very well preserved in evolution. So you can see here, it's a very famous picture of a monkey. And when our kids take the iPhone and look at operated with the home screen, this is what they do. But even kittens can do it. You can see here. Even humans can do it. But I don't know if you noticed, I'm a very serious scientist, so I went into the entire animal kingdom and found one example which kills the theory. But anyway, like all good scientists, I ignore it, and let's continue with the theory. But what is really cool is that congenitally blind, this is actually not cool, don't have, or any blind don't have access to all this information. But actually now they can have access. So you can see here Hamutal again. She's listening to the soundscape by the voice. And she's imitating. She's doing mirror system function. Now we put her in the scanner and let her do this, do reading, do face recognition, do object. And what is happening in her brain is really, really cool. What we see here is the probabilistic map of all the blind, congenitally blind, like Hamutal, that are doing object or doing a body analysis. And you can see that what she's activating this right extra-right body area, but also this A1 and the area around it because she's analyzing by sound. This is what happened in the sighted brain. There is nothing here in the auditory domain, but it's also activating the extra-right body area. And this is the overlap between the two, okay? And now we look not on the activation versus baseline, and you can see here that 100% of the subject, both congenitally blind by soundscape or sighted by vision, activate, this is the whitish pixels, 100% of them activates the extra-right body area. And now when we look at the peak selectivity of the extra-right body area, we see that the selectivity of analyzing the bodies versus faces or other objects and so on and so forth, reading, goes exactly into the same area. And actually, if we remove the tag, if it's a blind by soundscape or sighted by vision, we lose the ability to say who was doing who. The brain treats it as the same type of information because it's analyzing the shapes. Okay? I'm going to skip all this and run to the conclusion. This is actually a really nice set of work that's showing that reading center is activated exactly the same by braille reading. This is the peak across the congenitally blind reading braille and sighted. And again, the same picture that we got in the visual with the body, we see it with the visual word from area. And we actually found out a new specialization that we were not aware of when we started the experiment, this set of experiment, and found specialization also for numbers. I won't go into the entire detail, but basically in this experiment, subjects got the same stimuli, just like the FedEx example, okay? One time they had to judge what is the symbol, whether is it a V, an X, or an I. In the second task, they have to ignore this phonology and do the quantity, 1, 5, or 10. And in the third task, they have to ignore both the quantity and the phonology and have to say what is the color of the stimulus and ignoring its shape. And what we found was really amazing, and we combined it with some connectivity analysis that I don't have time to explain here too much, but what we found is the following picture. We found recruitment for the reading when they focused on the reading task, for numerosity in the other side, in the number form area in the right side. And if you think about it, it makes a lot of sense because this symbol is an O in one context and is a 0 in another context, right? And what is even more interesting is that we found out that the connectivity is different in these patches, both in sighted and people that were don't have a retina or didn't have visual experience. So the visual word form area connects to the phonology and the language system. The other homologous side connects into the parietal cortex, into the AIPS. It's an area that involved in analysis of quantity. The EBA connects to the body system, and so on and so forth. So to summarize all this set of data, I'm going to skip some a new language that is built on Morse, just to say that Morse is not activating the visual word form. But if you have a little bit of shape analysis, and learn this shape to phonology, you start recruiting the visual word form area. So to summarize, this is the almost one before the last slide. The visual cortex principle of functional specialization and organization can develop completely without visual experience, okay? And this starts to really get into a very deep issues of critical periods, how much the brain is plastic, how much do we need experience to develop this specialization. So this is one bottom line. And actually, I didn't have time, but all the brain areas that have specialization in the visual system that we tested show this phenomena. The second thing, and unfortunately I don't have time to show you a work that I did with Chris Satian and with Alvaro Pascualeone and Lotfi Merabet about object recognition. You can even have a person have their LO, the center that's doing geometry and recognizing objects recruited by Soundscape, but then you can do TMS and interfere with the activity there, and the person loses the ability to recognize this object, is congenitally blind using the Soundscape. You let wash out, and now they're able to do it, okay? And so on and so forth. The second point is that this can also occur in normally developed brain, in the sighted brain, in other words, to non-visual input. It can happen, I didn't have time to show you all the data, in hours to tens of hours, in some cases even in 2 hours, like I was teaching you to read. It can develop the selectivity in the visual world from not responding at all to the symbols. Now I'm teaching half of the symbols and half not. It will respond only to the symbols that I know to take that you know to take the shape and assign phonology. And the last point is that we suggest that this novel task-specific sensory-independent organization and plasticity is driven by a combination of connectivity biases, all this different connectivity that each patch of the brain have, probably programmed by genetics, by development factors, and so on and so forth, and sensitivity of each brain area to different task distinctive features of each area network. And this is true, this is a summary of all the papers and recent work also on the navigation system, exactly the same picture. And even in retinotopic areas, I don't have time to show you this evidence, but we can show, for example, that the fovea can be recruited by braille reading, but not the periphery of the system. So we recruit the system according to this computational power. For high resolution areas, like the center of the visual field, we will do high resolution things like reading. And for the periphery, we will use for low resolution things that usually we have in vision. In this case, it's navigation, okay? The last slide is to say that there is already a research, and we have a couple of projects running in the lab, in integrating now using invasive, but also maybe non-invasive. We can take a given sound or touch sensory substitution and couple it with novel sensory abilities like representing distance, like representing thermal analysis of the environment, representing infrared and vision beyond the walls, giving autistic ability to understand when people are approaching, but they still couldn't see them, to prepare them. So all this is an ongoing project, and this is a really exciting new frontiers where the animal studies and the human studies are starting to merge out. Okay, so I think I would stop here and thank you for listening and having so much patience, and the team that is contributing to this very multidisciplinary teams, MD, PhDs, engineers, computer vision neurologists, neuroscientists, and so on, that actually doing the hard work when I get to have Guinness in Dublin and get to know amazing people like the people here. Okay, thank you very much.
I'm not even going to ask for permission. I'm going to open the floor to questions just for a few minutes for anyone who has questions. That was the first one there.
Hi.
Great talk.
Thank you.
I have a question. When you showed that after the training, there was an encoding from the auditory system towards the visual system.
Yeah.
There was no frontal lobe activation that you showed at all. Was that lost? I mean.
No. Actually, it's a very good point. You have a very perceptive. We actually you can do this phase analysis in different time windows. And just for the purpose of the demonstration, we use the mask of the auditory and visual and all the areas between them to make the point. But actually, in the later phases, we get activation into both in motor and in prefrontal areas, which corresponds to saying what it is and the button press. So we actually, if you widen the window and don't use the mask, you would get also the hand area and the prefrontal cortex in the language area. Okay. So it's a very good point, but it's even like this, it's very complicated. So we used here a mask of the auditory system, visual system, and all the areas between them.
Yes, because just a quick follow-up. My point was whether in the early stages of training you have more cognitive involvement and then the encoding becomes precognitive.
That's a phenomenal question, and I will use this question to show one or two more slides.
This was
But
not
I'm going to
rehearsed.
answer the question, okay? This is this is all the methods we use and so on and so forth. Okay, so basically our approach is a longitudinal approach, and I want to use it to highlight two things that I think are very relevant to this community and are super interesting, and I think as a community, and especially in our area, we still don't have a good answer to it. And we think about, so the idea is that we are using longitudinal studies and scanning now the brains, I don't have a lot of data to show you, but a couple of it, in different points of time. So I want to highlight what are the different points of time. The first point of time is when you are perceiving the information on your body or in your ears. In the first couple of minutes, when you get it in the headphones or on your body, you feel the sensory experience coming from here. Then there is a process that is super interesting. It can happen in hours or tens of hours, but usually it's enough in hours. That is called distal attribution. At some point you realize, and your perception goes to this stage in which you experience information not coming from here or from here, but from here, from where you're looking. Like the example with the cane, that you start understanding that the door is there and coming from far away and not in your ear. This is a very interesting point. What is the neural correlates of the second stage when you stop experiencing it and experience it there? The second stage is even more interesting, and usually we use congenitally blind, or we study and we interact with congenitally blind, because scientifically it's a really interesting question. What happened when the system didn't develop all these selectivities by experience, by visual experience, can we develop? But we have a couple of subjects, for example, Pat Fletcher, when we worked with Lotfi Merabet and Alvaro Pascual Leone and The Voice and several follow-ups. And I think Jamie had a really interesting review about this. At some point, some of the subjects starts to develop, report that when they are taking an object or interacting with them or looking at you, they start to experience hallucinations. I'm calling it hallucinations. So for example, they would take the bottle and open it and look at it, and suddenly they would see something, because this is late blind, the people that used to see. Now there is a lot of interest in the news about LSD triggering hallucination. Could we make, actually the only advantage, or the main advantage of this 100,000 euro operation, it's a huge advantage over the sensory substitution, that is really cheap and very much more easy to learn, is that you don't have experience. But what if we will learn to do these experiences faster? That's one question. By some safe drugs, by brain stimulation, by smart, better training approaches. For example, now we have games that we develop so they would be more immersive. And scientifically, what happened in the brain in the second you start to experience this hallucination, this really visual experience that triggered by the sound, which is actually synesthesia. This is why I was so excited to come to this conference, okay? And later we can ask other questions. What happened when we're automated this process, when there is less cognitive load, which was your question, which I really used very badly to say a couple of slides that are in the extra slides. But thank you for this question.
Okay, there's another question here.
Yeah.
How long does it take for the category specificity in visual cortex to develop in the congenital blind?
Okay, so I'm going to use your question to show a couple of slides that are part of this collaboration with Laurent Cohen and Stanislas Dehaene. And yeah, I will repeat the question. The question was, how much time does it take to develop the selectivity for reading using a different sensory modality in a brain that never experienced vision? That was the question, right? I hope.
Not for reading, because they might have had braille experience, but for faces or other houses.
Okay, so let me show you for the reading, because they have the most extensive experience, including people that didn't have Braille experience. But actually what we did is to actually use this Braille and the fact that Braille recruits the visual words from area. And what we did is to develop this new language that is like Morse. As to remind you, Morse doesn't activate the visual words from area, but each letter is different by different shapes and different timbre and so on and so forth. And what we did in this experiment, and we also had an experiment in which we use it with the Hebrew alphabet for blind that never learned this. And we teach only half of the alphabet. And what you see here is the activation in the visual word form to reading letters that you know the phonology in Braille versus nonsense Braille. So you say it's not tactile driven, but it's driven by the fact that you know to do the association. And you see that there is no significant activity to the letters that we are going to teach them or to the letters we are not going to teach them. This is the first scan. Now we take them out of the scanner and teach them for 2 hours, half of the alphabet. In different subjects, we teach different alphabet. And we did it both for the Hebrew alphabet and for this new oval language that is like a Morse, that actually it's really cool because after Ronnie Albel showed that after 20 hours, they can read a whole tweet using this Morse in less than a minute. It's really cool. And now, only for the letters they know to do this assignment of taking the shape and doing a phonology conversion, there is increase into the levels of Braille. But to the phonemes that they didn't learn, the shape, the symbols, you don't get it. So in this case of reading, it can happen in as fast as 2 hours to develop the selectivity. We are now doing experiment in other domains. It seems that with objects is the same. With faces, we have the data of the pre-post scan, but we still don't have finished to analyze it. So I would say that in hours to tens of hours, each of these categories can develop without any visual experience.
Okay, maybe one last question where he doesn't have the answer on a slide. Jason?
Everything is on the slide.
Thank you. Thank you for your great talk.
Thank you.
The quick question is, have you looked at the cost on this cross-modal substitution on the sensor or the sense that's performing the substitution, like for example, hearing?
Wonderful question. I have the slide, but I'm not going to show you. But I'm going to use the slide that I already showed. This is a work by Nadine Sigalov, Shachar Mandenbaum, and yours truly, that was just published recently in Neuropsychology. This is going to a very deep question because in previous work, our lab and also Marina's Bendy's lab recently showed that for blind that are not doing sensory substitution, there is recruitment of the left visual system, including all these areas that I'm showing you, to process semantics by audition, to process language. We showed that it supports superior verbal memory, so they actually have much better memory than us, and so on and so forth. And what we did in this study is to check what are the responses to semantics before they start training, and what happened after. And what we, here actually, in this study, we report the after result. And what we found is the following thing. What they do, the task is the following. They listen to the word heel, like you did. Not really the heel, but one of the words. Then they are listen auditorily to heel or to a different word. Let's say hammer, okay? Now in the scanner, they have to report what they heard, so we can have analysis of their performance inside the scanner. And then, so they hear these words and they report, okay? And what is pretty amazing is that we found that, for example, in the visual word form area, that used to respond to this, hearing these words, heel or hammer, they have very strong activation during the analysis of the soundscape, but after 30 or 40 hours of training with this soundscape, now they are stopped responding, and actually they have a little bit of a negative bold, even deactivation to this hearing these things. So actually it means that there is very dynamic changes between task switching plasticity for a different function, which is actually very important, for example, for stroke recovery, and we don't know exactly how to manipulate it and to harness it for better therapeutics, and this is part of the study, and this task-specific sensory-independent plasticity, which seems to happen very quickly and in hours. So it changed the balance and the responses, in short, to the existing other modalities in this system.
Wonderful. Okay, in the grand old Dublin tradition, let's continue this conversation in a coffee house, i.e. here, and join us for a glass of wine and maybe further chats with Amir. Oh, it's upstairs. Oh, sorry, upstairs. Actually,
and for those who want to experience, they can come and have a drink and do the maze and have another drink and test the effect of alcohol on navigation. Thank you.
Please join me in thanking Amir for a fascinating talk.